of all the trends on the periodic table, the trend in radius might be the most important. You can rationalize all the other trends if you understand this trend in atomic radius. And we don't want to just memorize this. I see so many kids in first year chem that just memorize the atoms get bigger as you go down, they get smaller as you go across. That's not good enough anymore. We really need to be able to comprehend why the atoms change in size as I go across or down a group. And I want to be able to explain that. This would be something you'd find on a free response question that would be like a no calculator question where it's kind of like short answer or short essay questions. Now, in general, I think most of us understand that atomic radius increases going down a group, and this is probably the easiest of the two trends to rationalize. The orbitals get bigger as I go down a group. Going down, we said you're increasing in energy levels. So you could have a 1s orbital, a 2s orbital, a 3s orbital. Well, they're all the same shape. The difference is just that the electrons can be further from the nucleus, or in other words, this orbital encompasses a wider range around the nucleus. So number one, we've got larger orbitals. Electrons occupy more energy levels, meaning that they're farther from the nucleus, contributing to this increase in radius. Another thing that we should mention is called the shielding effect. If I have an atom, let's make this like a really rough sketch of an atom. So here's the nucleus, positive nucleus, and here are all my energy levels. Whoa, energy levels. Whoa, come back. We must have like a dead zone here. There we go. So this is a relatively large atom. And let's say I've got this electron way out in the 1, 2, 3, 4th energy level. There's my little electron. Now he's held to the atom by the fact that the nucleus is positive, the electron is negative. Opposites attract. However, as you get these bigger atoms, not only is the atom bigger because the electron is farther from the nucleus, he's in the 4th energy level versus the 1st or the 2nd energy level, but you also have more electrons. We call these core electrons. Core electrons are all the inner electrons. So like for example, the 1st energy level has 2, and then I'm just going to randomly scatter some electrons in the 2nd and the 3rd energy level. We'll throw another one in there too. Okay, so now here's the problem. Whoever came up with this name shielding effect, it was brilliant. This nucleus is going to have a hard time holding on to that outer electron in the first place. This guy is the valence electron. The electron in the outer shell, these guys, these inner electrons, these are called core electrons. So number one, this is a weak attraction. Weak attraction. Because the electron is just naturally far from the nucleus. But you've also got this junk in the middle. You've got these core electrons that are blocking the attraction between the nucleus and the valence electrons. So it's almost like the core electrons form a shield, and they make it even more difficult for that nucleus to hang on to the outermost valence electrons. So even these big atoms at the bottom of the periodic table are larger than what we might expect because of the shielding effect, where the inner orbitals and inner electrons form a shield, and they block the attraction between the nucleus and the outer valence electrons. So if you are ever asked, why is cesium a larger atom than lithium? I could talk about any of these ideas that, the orbitals are larger, the electrons are on average further from the nucleus, there are greater energy levels involved. But I would also throw in this idea of the shielding effect, that as I have big atoms at the bottom of the periodic table, those core electrons are going to block the attraction between the nucleus and the valence electrons. Going across the periodic table, unfortunately, here's the trend that people struggle with a little bit. Going across the periodic table, atomic radius generally decreases. And what people don't understand is this. Let's pick a group of atoms. Let's go boron. So here's boron, element number 5. And then let's go across. We'll do carbon, number 6. And then we'll say this is nitrogen, number 7. And oxygen is number 8. And then we'd have fluorine, number 9. And we'll end her with neon, 10. Okay, so here's a group of elements going across. I just randomly picked going across the 2p block. People will mistakenly assume that the atoms are getting bigger. The radius must be getting bigger because there's more stuff. You know, they're not complete idiots. They know that if I say boron is element number 5, the atomic number is 5, meaning, there we go, that there are 5 positive protons and 5 negative electrons. As I go across to neon, this should be 10 positive protons and 10 negative electrons. So they assume that, well, if you got 10 protons and 10 electrons, that should maybe take up more space. That should be a bigger atom. There's more stuff in the atom. And so then they have a hard time rationalizing why neon atoms are smaller than boron atoms. Here's a term that you're going to want to become obsessed with. I would almost put money down that somewhere on the AP test you will want to talk about this. Nuclear charge. Okay, so nuclear charge just refers to the charge of the nucleus. So for example, boron's nucleus, we could kind of say that boron's nucleus has a charge of plus 5. It has 5 protons. Neon's nucleus has a charge of plus 10. There are 10 protons. Okay, so here's one thing that's important. As I go across, I'm not adding an energy level. We're just filling the existing energy level. So for example, these are all elements that are filling the second energy level. I'm filling the 2p orbitals. I'm not adding any new energy levels, which is one thing that would make atoms bigger. We're just filling the existing energy level. So I might put that in here. We're just filling the energy level. So with these guys, I'm all filling the second energy level. Okay, so this nuclear charge term, think about it as magnets. I've got opposite charges that attract each other, electrons and protons. In boron, I've got 5 protons and 5 electrons, which would be an attractive force. Opposites attract. But as you move across to neon, you've got 10 protons in the nucleus and 10 electrons. The more protons in the nucleus, the greater the nuclear charge. That's like a greater positive attraction for the electrons. So these are both going to have attractive forces between the nucleus and the electrons. But this is greater attractive force. So as I go across, and I'm not changing the energy level, all of those added electrons are going into the same energy level as I go from boron to carbon to nitrogen all the way over to neon. Yes, I'm adding an electron, but they're all going in the second energy level. They're all filling the 2p orbitals. The most important reason why these atoms are getting smaller is because the nucleus becomes more positive. Greater effective nuclear charge means just that. The nucleus is becoming more positive, and it's going to have a stronger attraction to the electrons that are all in the same energy level. So if there's a greater attraction, atoms get smaller. It's like stronger magnets in neon versus boron. So I got to kind of think about that. Greater effective nuclear charge kind of means that the nucleus is more positive. And it has a greater attraction for the existing electrons. The stronger the attraction between the nucleus and the electrons, the smaller the radius of the atom. So I'd definitely be able to rationalize why the atoms get smaller. Use the term greater nuclear charge. Become obsessed with that. Trends in ion radius kind of make sense. In general, if you're forming a cation, a positive ion, it means that you've lost electrons. And now think about sodium. Sodium is element number 11. 1s2, 2s2, 2p6, 3s1. So there's the sodium atom. It's got one electron out in the third energy level. Well, as you go from a sodium atom to a sodium ion, well, this kind of makes sense. You're going to lose this 3s1 electron. So now you've only got electrons occupying the first and second energy levels. So if I'm comparing the size of a sodium atom versus a sodium ion, the ion is smaller. And that follows in general for any positive ion. It's usually smaller than the original atom. It's losing electrons. The anions are usually a little bit larger than the original atom. And sometimes, again, people just say, oh, because you're adding an electron. You know, if you've got a negative ion, you've added an electron. If you add something, it should make the ion bigger. Yeah, but in order to get full credit, you're going to want to talk about this. Think about, going across, and we can pick any group. Let's just make general p orbitals. 1, 2, 3. We'll call these just a random set of p orbitals. 1, 2, 3. And let's say I'm using chlorine. A chlorine atom might look like this. It would have 2 electrons in the outermost s orbital, and then there'd be 5 electrons in the p orbitals. We always said that electrons like to have their own orbitals if possible. Now that's not always possible. Sometimes you do have to pair them, but they don't like to be paired because like charges repel. So if I'm going to form a negative ion, that means that I'm adding an electron. And if I have to add an electron, so here's like this ghost electron that I'm going to add. Well, that's going to create a little more repulsion. And that repulsion is going to make the ion just a little bit larger than what you might expect. A little bit larger as compared to the original atom. So again, in general, cations, positive ions, are smaller than the original atom, and anions, negatives, are usually a little bit larger in radius than the original atom. And these trends follow on the entire periodic table, which we'll kind of look at in the next video.